Hi, my name is Marc-Antoine and I'm a TA for the Faculty of Engineering here at the University of Toronto. In this video, I will present you an overview of a typical engineering design project. So my goal is to make you understand the big picture and how the different parts of a design project connect with each other. Also try to realize how important that is to start a design project with a good systematic approach. This is pretty much what I want to highlight here, so let's get started. A design project starts with a project definition and it ends with the delivery of a prototype, along with its very detailed description, often in the form of engineering drawings. Most importantly, the design will have been validated experimentally. There are 4 phases to a design project, and it evolves from abstract ideas to concrete details. Already you may have encountered words that are not quite the same as you've seen before, and it's all okay. Different authors use different words, but they all refer to the same basic concepts or ideas. So bear in mind that I'm not contradicting what your prof might have told you previously. I'm only explaining it slightly differently. Although this process is presented in a very linear way, please remember that this is not how it actually happens. We often have to come back to previous steps. Sometimes it's even in the project planning, which is why we call the design an iterative process. Small changes during the iterations are okay, but major changes can delay the project and cost extra time and money. This is why we use a systematic design approach to avoid the major mistakes. A design project usually starts when the design team is given a project definition, also called a mission statement. It contains the necessary information such as what the product is all about, who it is intended for, and some key assumptions about the design. I will use the example of a Tesla Model S to illustrate the concepts that I introduce. The Model S is a luxury vehicle sold to wealthy adults. It was built around the assumption that it had to be fully electric. It is important to notice that this characteristic of the vehicle did not arise from the design process. In fact, this is a business decision, not an engineering one. There was a gap in the luxury car market, and Tesla tackled this business opportunity with the design of a new electric car. Now I will start painting a big picture of the design process, and in the end, it will look like this. Let's start with the first phase, concept development. This is mostly what you will do during APS 111 and 112. It starts with identifying the customer needs, which can be described as the customer's own description of a desired product benefit. So for instance, a Tesla owner could say, I love my Tesla because for me it is affordable, safe, and it has a great driving range. It's an important step because the quality of a product is often defined as its ability to meet the customer's needs. So if you do not identify the needs correctly, then the rest of the design process is rather useless. It is also important to prioritize the needs, because decisions will have to be made when 2 needs compete against each other. This is called a design trade-off. So maybe the Tesla engineers decided to put safety first, and then the driving range, and then the affordability. Not that the affordability is not important, but given the intended market, there can be a little bit more flexibility over here. At the end, it is not necessarily the selling point of the vehicle. The next step is establishing the functions, which means answering the question of what the product does. The Tesla transports passengers on road and highways. It may seem trivial, especially for a product that's already on the market, but it is still a crucial step, in part because it describes the boundary of the product, which means that it also defines what the product is not intended to do, such as going off-road. So we will not design for this functionality, and therefore we are more guided in what you incorporate into the design. Then we define what the specifications are. We describe what the product should or must be with the metric and a value. So we basically transform the customer needs into something quantifiable. For example, we may ask, how do you define a great driving range? Well, I want my car to travel 400 km on a single charge. Oh, thank you. Now I can do calculations with this. So here the driving range on a single charge is the metric, and 400 km is the value. But not all specifications are created equal. The objectives describe what the design should be, and the constraints what the design must be.
So if we transform the need for safety into specifications, a constraint would be to have dual front airbags. These airbags are required by law, meaning that if the car doesn't have them, it can't be sold. But the Tesla engineers took safety to another level. They said, let's have protection against side impact as well. So they created an objective that could look like this one. It was not required by law, but it became a design target based on customer needs. Not all constraints come from rules and regulations. It can also be an ultimate limit to a specific characteristic. For example, the design team could aim for a retail price between $80,000 and $100,000. But the project is not going to fail if the car ends up being $115,000. However, anything above $300,000 is a no-go zone because it totally misses the intended market. Often, those specifications can be determined by benchmarking competitive products in the intended market. So far, the needs, functions, and specifications were all solution independent. Beside the assumption that the car has to be electric and the constraint that it must have airbags, nothing has related to how we are going to meet the customer's needs in terms of what concepts are we going to use. That's very important. If you jump the gun and set up for a solution before it's time, you will restrict your design space and maybe miss an even better idea than what you set up for. But now it's time, so let's generate concepts. We can do this by answering how the product can accomplish its functions. The car has the functionality to hold all of its components together, so we can use a metal frame for that. And it has to deflect air from the passengers, so we can use body panels for this. However, we can also use a fancy carbon fiber monocoque to accomplish both those functions at the same time and even increase performance. So we have a choice to make here, which is selecting what concepts we are going to use. And this is what specifications are for. We know we have a price target to respect. So after estimating the price of the car with both those technologies, we can quickly disregard the carbon fiber monocoque, regardless of how cool it is or how much it would increase the performance. And now that we have our final concepts, let's start to assemble them together. You can see that for the system level design, I do not use numbers to divide elements, but letters instead. This is because the remaining design steps will be completed concurrently, and iterations are very common now. It is important for design to have an architecture. This is an assembly of all the selected concepts that we organize into systems, subsystems, and so on. For instance, the propulsion system of a Tesla is composed of an electric motor and a gearbox. When we build the architecture, we also establish a gross physical layout, and we start to think about space and dimensions. We also need to come up with another set of specifications, more technical this time. It is related to what the design should be in order to meet the target performances. So if we want the car to travel 400 kilometers on a single charge, then we have to aim for certain characteristics of the vehicle. Since we already selected the concept, it is okay now to be solution specific. And to validate that the technical specifications which is established match the global specifications we are aiming for, we need to do some calculations. And this is where we start to build mathematical models to represent the physics behind the vehicle. And after we are set with the architecture and the technical specifications, we can tackle the details of the design. This is really the most time-consuming and labor-intensive part of the design project. Two main activity types happen here, the modeling and the simulations. In the industry, we often call this design and analysis. We must first determine the details of everything, from the thickness of the windows down to the diameter, length, and grade of the bolts connecting the motor to the gearbox. Everything. Then we do simulations to ensure that the design will respect the technical and global specifications. For example, in the electric motor, we can simulate the mechanical stress and strain in the material, the vibration response to an impact loading, the magnetic field, and so on. However, those simulations can be very time-consuming, and we can never really be 100% sure of them anyway. So we must validate the design with physical experiments. This is what we do in the last phase of the design process, testing and refinement. We build prototypes of the product, and we do some experiments. We compare the results with technical and global specifications to validate the design. Then we can adjust the design if some specifications are not respected. Minor modifications in the detailed design are to be expected. It's okay. But if you have to change your product architecture, or use another concept, or even realize that the customer actually wants something different than what you thought, then things can get a little bit difficult. So we try to avoid this by using the systematic approach to engineering design that I just presented. And some projects will also use multiple validations at different stages of the design process, all that to ensure that the design questions are answered before it's too late. Remember that it is better to do small iterations throughout the process rather than large corrections at the end. When the design project is over, you deliver a prototype and its corresponding details, often in the form of engineering drawings, but most importantly, you deliver a design that has been validated with respect to specifications that represent the customer's need, which should ensure the product's quality. This was the big picture of a typical design process. I hope you get a better sense of the steps it takes to complete the design project. It's not really complicated, it's just heavily intertwined. And thanks for watching!